Hey, I'm JohnWrbanek. I'm at Glenn Research Center in Cleveland, and my collaborators, Susan Wrbanek, Gus Fralick, we've been looking into advanced radiation detectors for space for some time now. Pamela Clark has joined us as, uh, as our science PI for applying the compact full field ion detector system for CubeSat science beyond LEO. An outline of what the talk is going to be is, first of all, talk about the space radiation environment a little bit, what type of research technology development we've been doing, and the application for deep space CubeSats, as well as lunar science acknowledgments. Okay, space radiation environment in deep space. When you get outside the magnetosphere, the space radiation environment has a large variety of radiation sources. You got the solar wind, which is fairly low energy, but steady stream, lots of particles. Coronal mass ejections, where pulses of hydrogen and helium, some increased energy. I love this. And much greater numbers. Solar particle events, which are much higher energy pulses of hydrogen and helium. And then you got the general galactic cosmic radiation, which is a stream of ions going all the way up to iron, which much higher energy, but much lower concentration. All of these, the space radiation background changes planetary magnetosphere. Dynamic changes in space radiation background changes the planetary magnetic field. The higher the flux, mass, energy, the more penetrating the radiation through the magnetic field in the planetary body. CMEs cause by far the greatest effect in the planetary magnetosphere, but you can't ignore even the galactic cosmic background and any dynamic changes in that. Penetrating radiation modifies also planetary surfaces and atmospheres. This is why it's of an interest. In the Earth's atmosphere, you've got the heavy galactic cosmic ray ions are linked to a variety of conditions, of effects, aerosol production, unstable isotope production in the atmosphere, as well as ozone depletion, triggering lightning, lower tropospheric cloudiness, and long-term climate change. Outside of Earth, you've got GC ions linked to neutron generation in the Martian atmosphere, and also the space weathering of Mars asteroid spacecraft surfaces. These are effects that have been implied. There is a distinct lack of direct measurements in situ, but there's lots of models. People have flown radiation detectors. This is a sampling of some of the radiation-based detectors that have been flown. This is an eye chart, but these are all systems that are in flight or have flown. These are small-scale ones. These aren't the big monster AMS-type ones. The point of this slide is to point out all of these are based on silicon detectors. Where people are worried about radiation effects on electronics, we are worried about detecting radiation with silicon-based detectors. So the goal for what we want to do is to develop this radiation detector system that can fly on small satellites like CubeSats to reduce cost and development time. Our design point is, of course, a 1U CubeSat, 10 by 10 by 10, 1 kilogram. And so, yeah, CubeSats have currently flown in LEO, but as we all know, future for CubeSats is in deep space. When you get into deep space, you have a high particle influx from multiple directions, otherwise referred to as a spherical 4 pi solid angle. Something that's been referred to in other talks is that current radiation detector technologies need some sort of temperature compensation. And this is an issue when you're talking about the small platform size and power limits on CubeSats. So if you want to make a more complex system, you need new technology. So the solution, of course, is that you want a new, robust, low-power, thermally stable, solid-state radiation detector technology for omnidirectional measurements in a compact space radiation detector system. Our solution path is to pursue wide bandgap semiconductors and micro-optical technologies, which leads then to what has Glenn been doing for the advanced radiation detector technology research and development. We at Glenn have a history of expertise in facilities in harsh environment, thin films, silicon carbide, which is a wide bandgap material, the devices and harsh packaging, micro-optics, and space-based instrumentation. Let's see if I can do this without forwarding. We have in-house microsystems fabrication facilities. We can do thin films and characterize the thin films in-house, and we have flown on MISSI and other places, Pathfinder, our own space electronics, and this particular image shows a silicon carbide JFET that was tested on orbit in MISSI 7. Anyways, these strengths are being combined then into an in-house radiation instrumentation effort. Our concept car, as it were, our concept is the compact full field ion detector system, or CFIDS. This is a drawing. This is a drawing of the concept. It is designed for mapping heavy ions greater than 100 MeV per AMU, and this integrates. Love it. This integrates wedges for detecting incoming particles around a central Cherenkov detector. By using wide bandgap materials, we are designing for then high radiation flux rates for 10-plus-year missions. The original goal was, if we're going to go deep space, what's the harshest environment you're looking at? You're looking at Jupiter. So that's where we came up with that number. Low noise, multi-directional measurements at single locations. That's what you end up getting then with a compact spherical detector system. This concept is covered by U.S. patents by NASA Glenn. And yes, this is our concept picture. Okay, how this works. This is a cross-section of the sphere. And here's a close-up of the cross-section, where you have, in the sphere, you have the central integrating sphere, Cherenkov detector, and then these stacked directional counters. And the green outside are trigger veto scintillation detectors. This whole thing is sized to be 1U, 10-centimeter diameter. The general operation, how you sort them, because electrons should have been themselves in the first detector. These stacked detectors are a series of 4 LET, or linear energy transfer detectors, where they measure their signal returns, how much energy an ion or a charged particle implants into that detector as it passes through or stops. And then between them, you have absorbers, or moderators, if you want to refer to them as that, such that if you have an ion comes in and generates a signal in each detector as it passes through, it loses energy as it's going through absorber, and it generates a Bragg curve that can be separated then for different types of ions. Higher energy, over 350 MeV through AMU, then will pass through the detector completely and generate a Cherenkov light pulse in the center detector. Each of these stacked detectors are surrounded by a trigger detector on the front face to sense the incoming ion. It's just an on-off type of measurement. And around it, you have veto detectors. If a stray ion comes through, triggers the process, and then exits before it actually goes through the detector stack, then it rejects that event. Okay, we have been funded off and on, sporadically, over the last 5 years. We started with the radiation detectors in 2005, which in the AEVA, this is Advanced Extracurricular Activities Technology Project, and then went on to ETDP, which is Exploration Technology Development Product Demonstration, which morphed into AES, Advanced Exploration Systems. 5 minutes. OCT. Well, anyways, all the details are here. We've got some technology that we've developed, the silicon carbide-based radiation detectors, a dosimeter based on a silicon carbide diode, and a zinc oxide UV detector for the Cherenkov counter. This chart, this is an eye chart. Don't expect you to read this. The point on this is that we have, for the Cherenkov detector, the LET detector, and the scintillation detector, we have the state-of-the-art and a wide bandgap version of them. And for each case, the detectors would have less power draw, similar or better signal-noise ratio, and be able to handle higher temperatures, which means more robustness, and be essentially impervious to temperature changes. So this is our application for deep space CubeSats. This is the Wallops Goddard 6U, and then we placed our sphere in there to show you how it would fit. It would fit into the 1U volume. Signal conditioning electronics, charge integration, analog digital conversion, power regulation, data formatting, that would be another extra volume. We're thinking half unit, but this is very dependent on what bus you use and how it handles the data and communication. As such, this is very adaptable for 3U and 6U layouts, which are being discussed for operation beyond LEO. And by having a complex system like this allows you for unique deep space science using the cheap platform. Lunar science, as we're discussing here, Moon has no substantial magnetic field atmosphere. Measuring high Z, high energy ions from galactic cosmic radiation will tell you what processes are affecting the composition change, molecular structure, cause loss of hydrogen, the chemical aspects of space weathering. And here again, the implication is that a lot of these processes are implied, but direct measurements in situ or on orbit or on the lunar surface will help identify these processes and quantify the effects. And I like to end these types of with metri sunt necessare malum. The Latin for measurements are necessary evils. The models are wonderful things, but you have to take the data points. You have to take measurements. Otherwise, the models are just pretty pictures. Our summary, we're leveraging our in-house expertise for harsh environment thin films, silicon carbide devices, harsh environment packaging, factor optics, for space-based instrumentation, for advancing radiation detector technology. We're applying our wide bandgap semiconductors as radiation detectors, holding promise to realize the CFIDs. And the CFIDs, once implemented in a deep space CubeSat, will allow in situ measurements of HCE, galactic cosmic radiation interactions in lunar environments. Acknowledgements, lots of big people are involved on this, not just us four. Detector fabrication done by Elizabeth McCabe, Nicholas Verajay, Dr. Lanyu Chen, Joe Flatigo, Mark Krasowski, Dr. John Freeman, Dr. Stephen Birkenbell have been involved with shielding studies and general semiconductor modeling. Dr. Ben Malfors at Morehead State was wonderful in helping us understand the whole CubeSat systems and how we would generate some sort of proposal concepts. GRC Space Science Office has paid for my trip here. And Goddard Science and Exploration Directorate, specifically Bill Farrell, Mike Collins, and Wei Dao. Yeah,
right.
They've been super in supporting us with the proposal, and Roger McNeil at Morehead State has also been super in his support for our proposals in this area. If there's any questions.
Thank you.